Hi, we are a team of developers in Skychain Global. Uh, we do research on some medical databases and see some existing databases. And one of the recent famous database is the database of chest X-ray images, which consist of 100,000 images of X-ray rentgenology on well, and it have 14 different disease categories to each images. Each images is look like typical regional rentgenology image, and to be honestly, the only professional rentgenologist could read this image and detect some kind of disease on that image. And now we are trying to reproduce, to create some results of detection disease based on this data set and classify it on 14 disease. So most of the occurrences we have on this dataset is infiltration. We use deep learning methods, and during classification we also need weights all these categories. As a base, we used several articles, included one of the article from Stanford team and Andrew. They take existing neural networks for classification and use transfer learning methods to train existing, let's say, dense net on classification on these images and split it into classes. They also do some additional augmentation on that images for better classification. Also, it is possible to combine several classifiers to achieve better results. So here is the result. We use a TensorFlow as a platform, and you might see the training progress on the tensor board. So here is loss on training set, and during training we decrease a learning rate once we obtain some once we get stuck on the progress of learning, and after that we get a better learning. And also we don't have overtrained on our models, because on validation we also see a good results. We color with heat maps the last layer of our model, so we can see how our model is treat images. In some images and in some networks it works fine, let's say for dense net and for some categories. On the output we will see the following. Of course, the existing images as a base. Next we see a bounding box, because some of the images already marked with rentgenologist with the area of possible cause of disease, and Next we have a bounding box. Next we have we draw it with on the top of the images, and next we have a heat map, which is color map of last convolutional layer on the model, so it shows somehow the attention of our networks on the area on our network that last layer most considering it the most time. So let me run it. So it creates an inference on existing model. It is loading the dataset, and it is loading the model and draw all these images as I described before. So you can see the existing radiology images, the bounding box which is marked with radiologist, and our heat map. On some classes it's work fine. On it, let's say on pneumonia, it is shows there precisely, while on the other classes it is shown not exactly as in bounding box. So it depends on the classes and on the network we used. Also, we have the formal results based on the ROC and area under ROC for all of these 14 classes. So here is I run the inference on all this model. It is also loading the model, and on the y-hat is the results we obtain, and we will consider it with y, with tensor y, to show formal results we obtained. It is running on about 200 batches on a test split. So it is loaded because we have several models, and some of them are quite huge. So each image is processed in less than 1 second. And after it, we will draw the ROC curve for each category. So for each of 14 classes of disease. Okay. So here we get good results for some of the classes, and also say we have a good result for. We have a good result for, let's say, emphysema, and also we have some ideas how to improve this model. Actually, in the article of Andrew G and other scientists, it is claimed that those models, what we take it as a base, are better than radiologists, but we also see some way to improve them in terms of quality of results, and well, later we will show some other results from us. Thank you for your attention.